So, yeah. Yeah. So you'll pass the clicker to the person speaking after you. You'll pass the microphone to the person who's speaking after that person, because there are two mics. So that person's already getting mic'd up. Yep. Make sense?
Yes.
Okay.
Except for our order is not established.
Oh, okay.
It is, but it's not like, yeah. Also write it down. The first side is one side. Oh man.
You have to pass it back to me, and then I need to pass it off to Wisconsin.
So I should just, I really,
This is good. It might make sense for one person to be mic'd up the whole time. And then just.
there's 5 of us.
Yeah.
Oh yeah.
Worst case scenario, if you're like, oh man, we gotta get started. This person's trash. Yours and hopefully they'll put them down.
Did you figure it out?
Nope. There are 2 seats
Okay.
here. There are available. One next to me, one is Gary, and another one right behind me.
Yep, I think it's not worth it. Because like when you do this, it doesn't actually do this one like full screen. I guess I know a bit.
Yeah, I'm just gonna write down. I have a pen. Oh, is there a pen?
No? Pick me.
I'm just doing a final mic check here.
I'm on deck, so
Okay.
let me know anything.
Okay, thanks. Check, check. Check, check, check. Mic check. Check, 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 check. Check, 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 check.
I'm going to now, since you said it. I mean, you better laugh at it. You better be on the sending around a sheet, you know that we've been having a big push to try to help not only you guys get your careers, get the jobs that you want and so forth, but we're also trying to lay the foundations for the upcoming years. So we have one more sheet to pass around. We're trying to get a sense of where people are at, but also where people are going. So pass this sheet around, and if you could sign up on, not sign up, but fill this out, we would appreciate it. If you can just get it circulating through. And then we have we're going to be videotaping the presentations today. They'll also be posted. We'll get you some information about that. So if your parents want to see it, or if there's any other reason why you might want to watch your own presentation or share it with somebody else, you'll have that opportunity. What it will involve is 2 different microphones. And okay, so Eric's going to talk about that a little bit.
Whatever you're in the first group of, I'll just use them as
oh, okay, that's a great idea. Okay, so if we're ready for the first group, watch yours. Yeah, that's great.
Who's the first speaker?
Where am I going with this?
Okay,
Anywhere?
so flip that about 6 inches below your mouth, and then this you can either hold, or you can flip onto a belt. Or
I'll just hold it.
Yeah, probably easier. Speaker number 2.
I need a haircut so bad. Just think about to have like Matt Hunter be over here and then you would over there. Sure. Nah, it's fine. You're just looking at Dylan.
Yes, but I'm saying I don't want to go all the way over there.
If you want, we could. I mean, you and Hunter and Morgan over here and Matt over there.
Yeah, that's fine.
I had to give the mic off to you though, so that'd be weird.
So is the mic gonna
Yeah, we'll figure it out.
Either
way, it's gonna have to be transition to something.
2 microphones, you're gonna have to go from one side to the other.
Just put it. We'll just do us 3 on one side and then turn on the other. Done.
You're gonna laugh for a minute.
Alex and Morgan over there. That's fine. Yeah, no matter what. So you want to do the first 3 on this side and other 2 on this side, or where are we going? Yeah, we'll just go on that side.
I'll stay on the outside, so because you're gonna hand
I got a
off
break.
to me.
Yeah, I'm gonna hand it off
So
to you.
I'll stand over here, so I'm out of the way.
Okay, so who's speaking third?
This guy.
Okay, so you're first.
So first, second.
Yep.
Okay, guys, real quick, let's talk about how to hand off the microphones. So whoever's speaking first will be mic'd up, and the microphone should be about 6 to 8 inches below your mouth to pick you up. You can clip it onto a lapel, tie. For ladies, you can clip it onto a dress. Doesn't matter if it's sideways; it'll still pick you up. And then, really, unless you have pockets, you can just hold on to the body pack. Whoever's speaking second, the first and second speakers will already be mic'd up. The second person who's speaking is all set. The first person, once they're finished speaking, will hand the mic to the third person, because person number 2 is already set. Does that make sense? So that'll hopefully you guys have a couple minutes to figure out your presentation order like this group did. So be thinking about that. And sound good? Okay.
I want to hit the pick mute button. Pick mute. As always. We good? Knees on too? Cool. Good morning, everyone. My name is Hunter Fry, and I'll be presenting the Summit Automatic Shifting Mechanism with my fellow group mates, Morgan Mansky, Alex McCameron, Andrew Hinkle, and Matt Penning. Our advisor is Professor Will, and our customer is Professor Johnson. Today, I'll be going over our project description, going over our subsystems, our final design verification, and then some of the testing we did, the lessons learned from the project, and I'll wrap up with a summary. So as we all seen this multiple times before in all of our presentations, for our device, a user inputs a signal for our device that is 2 buttons. That brings the signals to the semi-automatic shifting mechanism, and the mechanism consists of 3 parts: the clutch actuation, throttle actuation, and the gear lever actuation. These 3 parts interact with the engine and allow us to make a successful fast gear shift. Here's our giant system diagram. In the top left, you can see the inputs into our system, into our microcontroller. We have our 2 buttons for shifting. Then we also have the engine parameters. We have the engine temperature, throttle position, engine speed, gear number, and vehicle speed. In the bottom right of the screen, you can see our 2 actuator assemblies. This top one right here is our shift actuator assembly, and the bottom one is our clutch actuation assembly. These are both run off the high pressure air tank, which runs at 3,000 psi. That has a pressure regulator attached to it that drops down to 100 psi, which the regulators run off of. In the top right, you can see our 2 screens that display engine parameters. Below that, you can also see our servo for throttle actuation. And this is all ran by our Mega microcontroller that's run off the car's 12-volt battery. Going over our subsystems, we have 6 main parts. We have our clutch actuation, gear lever actuation, the pneumatic system, throttle actuation, user interface, and then electrical system. Starting out with the clutch actuation, more specifically the pedal, you can see our old first design over on the left-hand side. We decided to change that for a few reasons. One, we found out that the spring out pedal was no longer needed since we have enough foot room already on the car. So we swapped out for the center picture here, which is just a small rectangular plate still mounted on there, which suffice for enough area to push the pedal. Also, you can see in this right picture is we added 2 stops to the pedal for the pedal not to go too far forward or too far backwards. This allows us to adjust the clutch in a way that whenever we're pushing, we are always moving the clutch cable.
So the second subsystem we're going to take a look at is the clutch actuator. The clutch actuator uses a pneumatic cylinder, a single acting pneumatic cylinder, to push this piece here, as you can see in the animation above, to pull the clutch cable and disengage the clutch. This uses a solenoid valve, which is electronically controlled by the microcontroller to deliver air to the pneumatic cylinder to cause the clutch to disengage. So you can see from the animation up here, when air is sent to the cylinder, it pushes the piston here, which moves this piece outward, causing the clutch to be disengaged. When the air pressure is released to the atmosphere, the spring in the cylinder, as well as the spring in the clutch, allows it to return. So the fabrication of this actuator went fairly well. There weren't too many issues. The only issue that we had was that during operation, some of the linear bearings in here would come out of their mounts, but they didn't have enough room to actually fall out. So the one change that we would have to do to that is just use some high strength epoxy to keep those in, rather than just using these set screws as you can see on top of this piece here. For the gear lever actuator, we use a double acting cylinder, meaning that the air pressure can push it either forward or backwards. You can see on this graphic on the right of the screen, when no air pressure is sent to the cylinder, the gear lever, which is shown in red, causes it to rest in a natural position. When the rear solenoid valve opens, air pressure comes into the rear of the cylinder, pushing the piston forward, causing the transmission to shift down, as shown above here. When the forward solenoid valve opens, air pressure pushes on the front of the piston, pushing it back, causing the transmission to shift down. The fabrication of the actuator went fairly well. There weren't any issues with it, but we did encounter some problems interfacing it with the transmission. So as you can see on the picture on the left of the screen, the original design, we had a rod end style connection, which would be offset to the gear lever, which is shown right here. We changed that up to a forked connection so that the piston in the cylinder would be in plane with the gear lever rather than offset to it to prevent any binding that would occur. We had some issues with it just not working smoothly, so having those in plane, there was no moment of the things kind of trying to fight each other, and it worked a lot more smoothly. Another issue we had with the gear lever actuator was the alignment of the cylinder itself. So when we first tested this system, the alignment, as you can kind of see here with the red lines, it was misaligned. So what happened was when we actuated that cylinder, it actually bent the shaft of the cylinder and basically rendered the cylinder useless. We got a new cylinder and just took a lot more care to get the alignment proper and straight and centered in the slot on the gear lever so that there wouldn't be any of that bending of the shaft, and it works smoothly ever since then.
So here's an overview of our entire pneumatic system. Starting over here on the left, we have our air tank, which, like we said before, holds air at about 3,000 psi. That then goes to a pressure regulator, which steps the pressure down to 100 psi, which is what our system needs in order to operate correctly. We then have a pressure release valve, so that in case the pressure regulator fails, it doesn't send 3,000 pounds of pressure to the rest of the system, which would break everything. We then have a ball valve, so if we need to do maintenance, take stuff apart, things like that, we can shut off the supply of air and not have to take everything else apart in order to take other components and do maintenance and whatever needs to be done. You can then see the air line splits off and goes to the clutch actuator here on the bottom, and then the gear lever actuator on the top. So in fabricating our system, most things went pretty smoothly. Initially, we had a little hiccup where the pressure regulator that we received turned out to be faulty. So that set us back just a little bit, but once we got a replacement, building the rest of the pneumatic system went very well. We didn't have any issues with mounting or airline fittings. Basically, all that stuff went very smoothly, other than the gear lever actuator, which you heard before, which was just a misalignment issue. The other problem that we had was what we had calculated for how many shifts we would get per one supply of the air. We had calculated we would get about 1,100 shifts. However, in our testing, we found that this was more closer to 600 shifts. And this is due to some leaks in the system where air could escape. Also, the pneumatic cylinders probably used more air per cycle than we had calculated. So that's why that number dropped so significantly. However, even with the drop in amount of shifts per tank, we still have plenty of shifts for the racing application that this vehicle will be used for. So in the end, it didn't end up being a problem. The next system is the throttle actuation. So we have a electronic servo which activates the throttle. And this is so we can perform rev match downshifting. In order to get this to fit correctly, it took several iterations of building a bracket, mainly in order to get the pulley on the servo aligned in plane with the throttle, and also avoid other parts of the engine so that it wouldn't interfere with things like the valve cover or the fuel system and could operate smoothly. Here on the picture on the left, you can see this is the servo mounted to the engine, and the red arrow over here is hovering above the throttle cable, which goes to the gas pedal in the vehicle, so that's how the user actually controls the throttle and drives the car. And then on the right over here, below the green arrow, is the cable which goes to the servo so that it can actuate the throttle. And as you can see in this picture, the two cables are going in opposite directions of each other. They're not interfering, so that when the user steps on the gas, it can open the throttle and doesn't interfere with the servo, and the servo can open the throttle and it doesn't interfere with the gas pedal. And then on the right here is just kind of a overview picture of the servo itself in the bracket, and then the little gray box is a voltage regulator, which we had to add into the system since the car runs on 12 volts and the servo needed 6 volts, so we had to step down the voltage in order for it to work correctly.
So our user interface has two LCD screens, 4x40 on the top, and it has this visual tachometer and the RPM in the top left corner. And then our second LCD screen, which is on the bottom of our user interface, has gear number, temp, and speed all listed, and that is a 2x20 LCD screen. So for this enclosure, our first iteration is on the left. It mounts to the front of the car's hoop, and this first print took 36 hours. So when we had to make modifications, we ended up changing it so that it looked like this one on the right, and that only took 9 hours. This is the original electrical system that we had. So on the left is our inputs, and the right is the outputs. So we had analog signals from the engine temperature, throttle position, a PWM signal from the engine speed along with the vehicle speed, and then the gear number, and then 2 buttons for shift up or shift down. This was all going to be run with a 12-volt battery, and then our outputs consisted of the LCD screens, a servo, and 3 MOSFETs to control the solenoid valves. So currently, we made some modifications this semester. So we ended up not needing the throttle position sensor. And then for engine speed, instead of reading in the PWM signal, we just calculated, ground speed. We ended up calculating that from the gear ratio of the transmission. So, and then we conditioned some of these signals before we read them into the Mega so that the Mega can process them properly. And then we added in an extra digital output for the shift light and to cut the ignition.
Okay, so for some of the final design verifications, I'm going to be going over some of the successes that we had. The first one was that the vehicle would consistently upshift upon the press of a button and downshift upon the press of a button. Going further, it would only execute one upshift upon the press of the button once. Even if the button was held, it was needed to release from the button and then press it again. And additionally, we added in a half-second delay to make sure that the driver wouldn't accidentally double tap the shift button and change 2 gears really quickly. The car was tested under a simulated road load. So basically what we did is we created a system of rollers that have a higher rolling moment of inertia, and that gives us a little bit more road-like conditions. The heavier steel tubes that are underneath the tires can kind of help keep the tires rolling when they start rolling, but also resist the initiation of rolling upon starting the car, which is good for engaging and disengaging the clutch to be the most road-like. Additionally, the gear, speed, and temperature were accurately displayed on the screen. I'm going to be talking a little bit more about some of the challenges we had with this in a minute, but once the car was started up, it would display these properly. And then finally, the shift light functioned properly. So basically what the shift light was to inform the driver of the optimum time to shift in order to stay within peak power of the engine. This light is able to be changed at which RPM it actually comes on at, but we usually keep it about 500 RPM below the max RPM of the engine. So some of the shortcomings that we had with our project, the LCD screens didn't display the visual tachometer appropriately. When we used a tachometer function in the code, it worked well. However, reading in the tachometer reading in the engine RPM from the car, we were having some problems. Before executing a shift, it would work properly. However, once a button was pressed to execute a shift the first time, it would have a lot of distortions. You can see the second line is shifted over, and then some of the characters would become messed up. And then for each consecutive time the button was pressed, we'd get a little bit more distortion. And then the shift buttons were also not mounted to the steering wheel. That was another something that fell through the cracks that we just kind of weren't anticipating, kind of forgot about from our SDRD that it was something we were supposed to do. But luckily our system was still able to function appropriately. And then one of the bigger challenges that we came into was that the rev match downshifting didn't work quite properly. Like the RPM display, we were able to control the servo from the code. However, when we integrated all of the different portions of the code together, we had a hard time getting the servo to actuate upon the press of a downshift. So that's just something that we're going to be looking into for the future and seeing if there's maybe another easy way we can go about doing that. And that's something I'll talk about later as well. So for testing, we had 2 really major components that we needed to meet. The first was that the system needed to be able to execute 100 shifts without missing a shift. Luckily, we got this on the first try, and we kept going from there and still didn't miss a shift. So that worked out really well. And then second was that we needed to be able to complete either an upshift or a downshift within 1 second. Both needed to be done within 1 second. And you can see here, we are way under the 1 second mark. To test this, we used a slow motion camera at 240 frames per second. And we did an average of 10 shifts for each one. And then looking at the slow-mo, we were able to see when for the upshift, we were able to see when the actuator was engaged and then when it returned to its home position. And then for downshifting, we were able to audibly hear when the clutch was re-engaged at the end of the cycle. So these times, under a quarter of a second and about 0.4 seconds, we believe these could be further optimized by even a tenth of a second, and this would bring us a lot closer to true Formula One shifting times. So I'm going to be going over some of the lessons learned. One of the first ones was the breakout board. You can kind of see our rat's nest of wires over here. We ran into a lot of problems with the stiffness of the connections, the gauge of the wires, the size of the boards and solder joints and things like that. So we believe that cleaning that all up and making a single breakout board that can kind of contain all of those would really be beneficial. And then testing the car, we think that testing some of the subsystems sooner might have given us a little bit easier time integrating each individual one with the whole protocol. We were able to get a lot of them to work kind of individually on the bench, but then when we tried to use all the systems together, we ran into a lot of problems with misplaced ground wires and things like that. And then not overcomplicating was a big one. I'm sure that's a lot of teams ran into things like this. Hunter mentioned before with the clutch pedal. The spring-loaded clutch pedal was a great idea. However, it was just one more level of complexity that we didn't need. So removing that just kind of gave us that much more room, that much less complexity in the front of the car. And then the rev matching, upon discovering that our servo wasn't working appropriately, we determined that there might have been an easier way to rev match just from changing the engagement time of the clutch upon the downshift. And then double-checking electrical connections. You can see over here, just due to a misplaced ground wire, we kind of exploded our first servo motor. And that was just something that, attention to detail and just double checking our work kind of would have helped beforehand, but just double checking that. And then watching for electrical interference. We had some problems with our fuel pump, when it was working, and then when the servo needed to draw power, we were having some interference. So looking into that beforehand might have helped us just implement some capacitors before we needed them. So then for a summary, we went over our project description. We went over all of our subsystems that we worked on through the semester, our final design verification, and things that were met, and then some of the things that we struggled with. We went through the testing, and then the lessons learned. And I don't know if we're doing questions or not. What's our LY?
So you demonstrated last week that it's working fine, everything is working, but I have a question. If you want to redo your project, is there any subsystem you can approach it in a completely different way? Like, I don't know, completely redesign one of your subsystems for future generations?
See the screen and the servo? Okay, so yeah, I think, so the question was some things that we might redesign for a future iteration of this project. And I think unanimously we kind of agree that the servo, that's something that we would like to do a different way, as well as the screens. I kind of mentioned before about the re-engagement of the clutch. That was something that the team kind of talked about after the fact. Just changing the time delay, so when the clutch is re-engaged, you can re-engage it at a point that is basically the same thing as doing rev matching. So that was kind of a big thing. That's fair. What do you guys want this one?
The mic.
Oh.
You can use the thing. Yeah, so one of the ideas we had for changing the rev matching, so instead of using the servo to actually activate the throttle, basically there's this phenomenon when you disengage the clutch, if there's any input still on the throttle, it's going to spike in the RPM. So essentially, say you're releasing your foot off the gas pedal as you're hitting the downshift button, the clutch is going to disengage so quickly that you can't get your foot off the gas pedal. So you're going to have a spike in RPM and this thing called rev hang. And as the RPMs are hanging at a higher RPM, they're going to slowly start to come down, and you can just re-engage the clutch once the RPMs come back down to whatever target RPM you need. So that could have been something that we could have done instead of actually opening the throttle to try to hit a target RPM, we could just wait for the RPMs to come back down to whatever it was we needed, and then re-engage the clutch.
Any other questions? Awesome, thank you. Oh, I should probably just stall till you win. Can you log in?
So, yeah. How do we want to introduce ourselves? We're not going to. All right. I'm going to say scratch. Yeah, sure. Yeah. I'm going to introduce everyone. I'll just introduce everyone. So this goes like. You said like, yeah, okay. I don't really want to be heard. So. I'll do this. Good? That's fine.
You're going to have to walk over here and pass it off. Or
That's fine.
In the middle?
Yeah, sure.
I mean, you got your videos. Since they're over here. You have your videos. Yeah, you're going to go over suits. I know. I'll sit down here, just finish up.
Yeah, this is going to be fun. Okay. Yeah. You gonna start first? Cool. Yeah. Oh, he's got it first. Good morning. My name is Robert Hemmerling, Robert Heffley, Winston Olson, and Michael Balsterzak. And today we are presenting the final oral report for the Smart Lock Senior Design Team. So our presentation today is going to consist of an overview of our entire project from the beginning. We're going to start with our project statement. Then we're going to go on to some preliminary designs and how those designs attempted to accomplish our goal statement. Go into our finalized design, what we resorted to at the end to best accomplish our goals. Then the results of testing our final plan, the accomplishments, what we succeeded in our testing and where we fell short, and then improvements for the overall project. So our problem statement, develop a system that will allow a user to unlock a thumb turn from a remote location. Our customer was Professor Pete Johnson. We met with him at the beginning of last semester to discuss the scope of the projects, what requirements he had for the projects, and what he expected of us. We came together and created a system design requirement document that complied with his requests. After creating the SDRD, we created our goal statement, which was to create an add-on to a traditional deadbolt lock that allows users to know the locked and unlocked status of a deadbolt lock and manipulate the locked and unlocked status from a remote location, on top of maintaining the traditional functionality of your thumb turn. Some additional requirements was to make the door or the application controllable via a mobile app and web application, accessible by a password-guarded account, so add security functionality to it. We wanted it to remain relatively quiet at 50 decibels from 20 feet away. We wanted to have a variety of color palettes, and we wanted to not damage the door upon installation and removal of the system. So to begin with our goal statement, we used an alternative solutions analysis to determine the best solution for all the different subsystems that went into our project. In particular, the microcontroller, the housing design, the driver, to the thumb turn, and the adhesive. We basically decided what important aspects we wanted from each subsystem, and we weighted those and determined how well each of them succeeded in accomplishing our goals. I'm going to turn it over to Winston to talk about the electrical portion of the design.
When considering the original electrical components and circuit design, there were two main things I had to take into account, which was the power system, as the Raspberry Pi and analog digital converter required 5 volts, but our battery ended up being 7.4, as well as the control system, which operated the servo and communicated with the database. And finally, the web and mobile applications. In the original, we had a micro USB port, battery charger, and a buck converter. Micro USB was going to go through the battery charger, charge the battery, and as well as power the circuit at the same time. However, there were some problems with this. First was this buck converter. The output was not always 5 volts. It had a tendency to change along with the battery voltage. And as a result, we lost 2 Raspberry Pis and 2 analog to digital converters. So the solution was to get rid of it and got a buck boost converter. It is able to maintain a constant output voltage, which is always 5, which is ideal for the Raspberry Pi as well as the analog to digital converter. The only issue with it is about 4 times the size of the original converter. Also, the micro USB port was gone. We replaced it with a simpler power jack, mostly because it was challenging to fit the USB port into the housing. The power jack had enough depth that it was able to go through it. And we also had some stuff that never ended up being implemented, such as this servo shutoff and power save relay. We had to wire a additional wire into the servo internal potentiometer to be able to achieve feedback, so knowing whether the door is locked or unlocked. And if it was powered down, we would never receive a signal over that. Also, the servo protection current motor or mirror was never implemented either, as it just drew extra power. And then the servo movement control was an additional circuit to interface between the Raspberry Pi and the servo. And again, we ended up just connecting the servo directly to the Raspberry Pi. The things that survived were the Raspberry Pi 0W, which is the brain communicating with the database, as well as reading the ADC and the read switch. The ADC read directly from the servo motor, and then a 7.4 volt battery. This is the final schematic. I understand it's kind of hard to read that we ended up with. There are some new components on here that I will show you. The first was that read switch. That component directly tells us whether the door is opened or closed, as well as not allowing the door to lock if it's changed to a locked state but the door is open. Also, the feature that kind of didn't work was the warning user of the break-in. That's also what that would have been used for. Next are these 1 millifarad capacitors. When we ran this first on battery with the new buck boost converter, every time the servo tried to operate,
it would actually cause the Raspberry Pi to restart. And after doing some investigation, we realized that it was overcurrenting the buck boost converter. So I started adding capacitors one by one until when I operated the servo, the Raspberry Pi didn't restart. And finally, the power adapter that was on the side plugged directly into the front of the buck boost converter, the input side. Our battery life from the original, which had about 92% efficiency, was probably about 10,617 unlock cycles. As you can probably guess, it never ended up being that. The new buck boost converter had an efficiency of about 80%. I tested at about a 200 milliamp load, and the battery ran for 17 hours. That's with no operations of the lock. And then when we tested with operations for about an hour and a half, 730 cycles, about 50% of the battery was remaining. So the new estimated cycles would be about 1,460. The mobile and web application can unlock and lock the deadbolt. It shows the position and indicates if the door is open or closed. The main problem with it is that the login screen was never implemented, so there's absolutely no security on your smart lock. So in summary, the external power connections were changed. The reed switch added functionality, letting you know if the door was open or closed. Additional components were needed. Expected battery life dramatically decreased, and the application has zero security. I'm going to pass it off.
So, preliminary for our mechanical systems, we wanted to determine how much torque was going to be necessary to turn the deadbolts, so we could order the right servo or have the right drivetrain for it. So as you can see here, our maximum torque, well, basically what we did was we added a lever arm to the thumb turn, and then we progressively added more mass until it was able to actually turn the thumb turn. And one of our deadbolts was particularly hard to turn, and the maximum for that one was 37 ounce-inches. So we knew that we could not have a servo that was going to be any less powerful than that. So what we ended up selecting was this HS 485 HP servo. And what was nice about that was that it had 66 ounce-inches of torque at 4.8 volts. So that was going to be 1.8 times what we needed at most. So it was going to operate, be possible to operate at 5 volts, which was nice for the rest of our system. It was compact. It was only about 1.6 ounces, which is not very significant. And the potentiometer feedback was really important because then we knew if it was going to be locked or unlocked. So originally we were going to use, to actually connect to our thumb turn, which is seen here, it's going to be a plate with a bunch of holes that were threaded so you could add pegs to each specific deadbolt. And so we thought that that would be really modular, but unfortunately that was not going to be very easy to install because we wanted a system that was going to be very simple for the user to install, even if they're not mechanically inclined. So what we decided to do was have 3D printed linkages that would fit each specific deadbolt that was required by a customer. And originally we were going to have a small little peg to put in here so we could have, so it wouldn't just be the spline from the servo, and it would increase the surface area on the 3D printed parts since it's a little more fragile. But instead of doing that, we decided to just use the actual servo horn that came with it. And we did that because then we did not have to manufacture a spline into a square block of aluminum. And it was one way we knew that we weren't going to damage the spline by having a material that was going to be a little bit harder than the actual drive shaft of our servo that we purchased. And it was also going to be cheaper for us since it's free for us to 3D print these components. So then originally for our old housing design, we were going to have a symmetrical slot, so it was going to be installed where the deadbolt was turned halfway. But instead of doing that, this was honestly only because of aesthetics. So we decided to just have it started in the unlock position, and then it was going to be rotated from 90 degrees to lock it. So it was just basically to ease installation. And then here, this is where our servo actually connects to our housing. And instead of just having them be tabs, we just extended it longer so that we'd be able to have a little bit more security of a housing and not have to worry about these tabs breaking off under torque. And then we also added these covers so that we could, to be more aesthetically pleasing for our electrical components and our servos, so they wouldn't be exposed and there wouldn't be anything that would be able to jam it. And we also added a snap fit to that after about our third revision so that we wouldn't have any jostling when the doors open or close. And also for our third revision, we added our power jack because we had a little bit of change in plans for our power supply. We added a hole to route the wiring for the potentiometer and the servo. This was actually just for the installation of the servo. We didn't know, we didn't realize because before we had to do some post operations on our housing in order to fit the servo through. And then there's also a hole which is not visible right now for the magnetic reed switch, just the wires that go out to that. And this is basically just how the servo goes in. There's just 4 screws that go into the tab there. And then the linkage goes on top of the servo. And finally, one of our final changes that we made to our adhesive, or to our mechanical systems was our change from our adhesive, which Mike will tell you a little bit about later. Originally, we used double-sided command strips, but we found that since the tabs weren't accessible, ordinarily how you take these off is that you pull the tab straight down and it stretches the adhesive out so it's no longer stuck to what it was originally stuck to. But we could not get our housing off without prying it off, which you guys saw, that little dent that was in the doors because we used a screwdriver to take our housing off. So we switched to Velcro strips. So that means that we can take the housing off the wall and then the tabs would be visible, so it would be removable without any damage to the door whatsoever.
Okay, so I'll be talking a little bit about some of the testing that went into our project and the 7 different tests that we did. So this is just a layout of what's to come. All right, so test 1 was supposed to work with the mobile and web applications. So with that, we were trying to require a person to use the web interface and then download and operate the app itself. And then on top of that, we were supposed to be able to identify the lock status by logging into each respective interface. So with that, that was one of the shortcomings of our project. I'll touch on it in a few slides, but we, as most of you know, we had a former member of our team who was very, very skilled in this area. Winston is very skilled in a lot of areas. This was not the best one for it. So we were lost. He was the best at it. So we definitely tried to implement it, and we tried to do as much research as we could. It unfortunately didn't come to fruition, so I'll be touching on that in our shortcomings slide coming up. So test 2, like Bill was saying with the adhesive, we had to change out our adhesive because before we were using just like the regular stick-on 3M command strips, and that had a little bit of problem when we were trying to get those off the door. We've since moved over to the Velcro adhesive, and that is working out a lot better. Even during shooting of our video, we were still able to use a lot of the Velcro adhesive strips, and it has been working out great for us. So with the second test, it was to pull the class. In talking with some of the other members of the later section, because we revised the poll that you guys took, and we gave it to the later section. So this was what they received as well. They did, however, get the correct answer, but we were, upon further investigation, asking them what they really would have preferred. If they had the option to choose that both looked the same, they would have chosen that. I had talked with almost all the people in the other section, and that's what they came up with. They just guessed, and it just happened to be a lot of them guessed the correct answer. So another aspect of our test 2 was that there is a battery charging area. Bill showed you that we did adapt that there to be a plug for accessibility to the battery. So that passed, and then one of our SDRD requirements was that the whole component itself, the system its entirety was to weigh less than 3 pounds, and it came out to 1.75 pounds. So test 3 was so that it did not make a lot of noise. Mainly the requirement was so that it did not wake up Professor Johnson's kids if he was actuating it at night. So we adapted the test to make sure that it was under 50 decibels from 20 feet away, which it was 9 decibels underneath it, so it definitely passed. And then we were able to find 3 different color palettes for a wide variety if you wanted to print the housing in different formats so that it could seamlessly integrate with any door, so that it would look aesthetically pleasing. All right, so Winston's going to be playing a video for you guys, and I'll describe it a little bit. So test 4 was on the battery and feedback. We were tasked with remotely locking and unlocking, and then manually locking and unlocking the system itself. And so Winston wrote a code that it would automatically count. So that was an awesome hour and a half to watch. And then we also manually went through all the cycles. So it worked out very well. There were no hiccups or anything. The locking mechanism works without a hitch. And then we were able to indicate and relay the status of the lock. So the reason for this this box right here, in case you guys cannot see it in the back, it says what did and did not pass on this lock. So next slide, please. It wasn't actually waiting for me. All right, and then so we were working with keyed locking and unlocking, and that was to cycle through it 50 times just to make sure that it was able to lock and unlock. Next slide, please. Test 6 was a lot like test 4, and we saw that application every time we were moving it around. But if you wanted to see test 6, pretty much go back to test 4, and it's all pretty similar for the output. And then what we were doing, we were load bearing, so we wanted to make sure that it would be able to hold the different weights in the X, Y, and Z directions. So some of our accomplishments were we passed all but one of the SDRDs for those that are tested. This is just like a small layout of some of the ones that we did test, but here are some of the shortcomings. Test 1 was the section that we were not able to test, and that was so we can't necessarily count it as a failure because it was not actually put up to a test, but we did list it on the shortcomings. And then test 2, when you guys, everybody guessed correctly, that's awesome, that's on you, that was on us too. So that was also part of our shortcomings. So I'll turn it over to Bobby.
All right, so to talk about some improvements, where we could have improved the final design, we could have used a different microcontroller and simplified the controlling process. We could have pursued further development in the web and mobile application, implement security features, and basically make the system more secure online, improve power consumption so the battery has longer battery life, develop a more universally applicable thumb turn, and design a smaller housing that wouldn't interfere with door frames or protrude too far into a room. Some key takeaways: we learned, we got better at interdisciplinary collaboration, working with another electrical engineer and even working with other mechanicals with different interests from ourselves. Mastered critical thinking and problem solving. We came up with this design from scratch based off of an SDRD. We documented everything according to the requirements and organized all the documentation, and we learned how to design and implement our design. So in conclusion, we talked about some of our past designs, our final design, the results of our testing, and improvements. Thank you for your time. Any questions?
John?
How do you measure how loud the lock was? We had a microphone that we placed 20 meters away, and we used Audacity to look at the peak from like clicks over.
one, anybody can literally lock or unlock your lock from anywhere if they know the database link. Next, you can't actually see, for example, where or when the lock was locked or unlocked, and it doesn't send you any push notifications. You kind of just have a fancy deadbolt.
Professor Johnson?
So you mentioned that you did a test on the battery, and you did it to the battery's 50% level. Are you assuming that it was going to repeat that performance of the remaining 50%?
Well, that 50% was after we had done the 730 turns for our testing. I went and looked back at the battery voltage and determined it was about 50% of its remaining life that it had used.
We never test the battery to failure. Yeah.
So you're assuming then that the remaining 50% will repeat that same performance?
Yes, that is an assumption.
So that's basically just an observation. There was never really a requirement to find out how long the battery would last.
Are there any other questions? Brett?
What was the weight, how much weight did you put on the housing to check if it withstand that?
So the question was, what were the weight, the load bearing tests? So in the X, Y, and Z directions, so X is those are all specified in our test plan and test report, but X would be in so if you have the door here, X was down, Y was sideways, and Z was like trying to pull it off the door. So X was 15, Y was 15, and Z was 5. Are there any further questions? Thank you for your time.
I just really close after.
Yeah.
Michael.
I didn't capture your title slide, so you can just pull up the title slide real quick. That'd be awesome.
That was rough. I did not.
I went a minute and a half over. He went 4 over where he's supposed to.
I didn't know that
You just looked down.
I know. But like, why would you look down in a project that you're supposed to be making eye contact with people?
I just briefly looked down twice, and I was like, oh, I went over.
I did not know that. Come on.
Here, we were
You want to start back there?
Just long enough for me to capture it. Yeah. Pushing it until that goes away. Okay. Got it. Cool. Nice.
Oops. I just signed out. I mean, you're signing somebody else's account.
Yeah.
Good morning.
How you doing?
Alright, I'll be the first one to.
Okay. I'll give you this mic. Change the channel on this one.
So what I'm gonna do is this, you need to keep this attached to this at all times. So it's a clip. What you'll do is you'll clip it, and you can just put it like I put it right here like this. And then I put this in your pocket down there at the bottom.
Okay. You don't have to put it in your pocket.
But then once you're done talking, you give it to Ryan.
Yeah.
Yeah. So you're giving it to Echo, I'm giving it to Jasper. Echo, you're giving it to Ryan. I am giving it to you. I'm giving it to you. You're giving it to Jasper. Okay.
Then I'll go back to one.
And then Echo, you hand yours to Ryan. Check. Test. Well, so I should be over there. You should be over here. So when I'm done talking, Echo will come over. So, he's second. He's third again. So Jasper, you're over there with me.
Yeah, those two of us three.
Yeah.
Alright, hand this to you.
It should. I can start off, and then I can.
The 8 inches.
So like putting this
one video on either side.
You're on this side. Because you're handing off to Ryan. You're third, right? Oh, I'm handing off to Echo. Or I didn't switch there. Echo over here.
Cool. We'll make it work.
Yeah, he'll come over here. You'll walk over there.
I'll switch.
Can you unmute the PC? Unmute the PC.
Yeah.
Good morning, everyone. My name is Matt McGinnis. Up here we have Echo Yin, Landon Rosenboom, Jess Rector, and Ryan Taylor, or Ryan, Pitcher. Sorry. We are the Telepresence Robot Group. Our advisor, Professor Alhawai, and our customer is Professor Kabali. Brief outline of our presentation. We'll go over the goal of our telepresence robot. We'll go through our system design requirements. We'll hit each subsystem, mechanical, electrical, and computer, do a brief overview of what we've changed since December. We'll do a test overview, or some additions that we could have made if we had more time, some summary at the end, and then time for questions. So the goal of our telepresence robot was to give any user the ability to access our robot at a remote location and be able to drive it anywhere inside of Galveston. So some of the system design requirements, we came up to meet this goal, where we wanted to have control of the telepresence robot from a remote location, obviously. We wanted our camera gimbal to mimic neck behavior to give a more natural feel. We wanted to provide a user with a login, driving interface. We wanted the battery to operate throughout the span of the workday, and for the entire robot to operate throughout the span of the workday. And we wanted the robot to be capable of maneuvering all on flat surfaces. So in December, this is the design that we came up with. And then at the end of our semester here, we approached this final design. And now Landon will go ahead and tell you more about what we did.
So, so starting with the kind of the meat and potatoes of our design. So the stem structure, what is holding up our monitor, our soundbar. So as what we came up with at the end of the last semester's design, as you can see, we have the 2 side stems within one middle stem to the back. As you can see, the monitor is only being held by these brackets here, and the side stems aren't actually connected to the center stem. So we decided to change not only this back stem design and make it into 2 front support stems, but we also, for our final design and what you can see on the robot now, is this back plate that also connects the side stems to the center monitor and the center stem. We also got rid of the 2 top brackets. We realized they weren't important now that we had the horizontal bar giving extra side-to-side support, but we did keep the lower brackets to help reduce some of the wobbling motion from side to side when it turns and stuff, and to give it kind of a fail-safe. So here's some of the intermediate changes. You guys have seen some of these before. So originally when we first went to this front 2 angled front support design, we were just going to have this all welded. So in here, this was all going to be aluminum. And then we realized, well, none of us have ever welded aluminum before, and we figured this would not be the time to learn. And we figured that welding is going to make things pretty permanent. So we decided to come up with a design that's more manageable when it comes to taking apart and making changes. So at the bottom, we changed all the bottom plates to steel. The collars over here to steel as well, and made them longer so they can be bolted through. They're welded here, as you can see on the robot today. We also created front plate that is welded to this base plate, and all of this is bolted through. And then up here on the stems, instead of having it welded, we have this collar design. All of this was manufactured fairly well according to the pictures and the design. So the next mechanical thing, one of the last things we tackled was the electrical component case. This is the case that holds the battery, the PC, the converter, inverter, all the stuff we have. Originally we were going to 3D print it, but then we realized that we cannot physically 3D print it, I believe, with all the with the size of it and what we're given in terms of 3D printers. So we decided to make this acrylic, laser cut, and then glue it together with adhesive. And we also changed the front hinge door to a top sliding door, so it's more accessible from the top and easier to work on the components inside. And here's the finished product. And yep, I'll hand it over to Echo now.
So we also did some changes to the camera gimbal. So on the left is our old design on the camera. As you can see, the motor is directly mounted on the support tube here, and it will drive the gimbal by the gears and belt. On the right side is our current design. So the motor is mounted on the outside of the gimbal in this square here and connects directly to the inside by this cross shape. Later I will show a clear picture of it. And here are 2 modifications in our design process. So on the left is our first draft. It is very rough, and all the parts are very thick. So it is going to take a long time to print. So we upgraded to the second modification on the right. This one is much more like the final design, but it still has some issues. So in the printing process, we have some difficulties. The first one is the terrible printing quality of the printers in the manufacturing lab. So when we try to print this part, it always messes up with this cross shape here. And we also experience some weird problems, like the printer stopped working and the top structure of the part shifted. So we have to use one of the printers in the First Plus lab, and that takes us a long time to print. Also, in the second modification, we came up with this support tube with 2 concentric circles, and we found out that it is impossible to remove the support material between them. So in the end, we just replace it by this simple square here. Also, in the second modification, there's no extra room to mount the motor on the gimbal here. So we just make the left side of the gimbal thinner right here to leave extra space. And we also did this square shape here to allow the wires of the motor come through here. So we also designed a new support bracket. In the old design on the left, we have 4 support brackets here mounted on the front side of the main structure. However, when we put on the monitor and soundbar, we found that there's no extra room between the soundbar and monitor here. So we designed this new bracket which is mounted on the back side of the main structure and attached to the soundbar to fix it.
So
I'll be going over the all the electrical components and electrical design today. And the electrical ones that we had to use in order for our project to work was the 12-volt battery, the DC to AC inverter, the Arduino Mega 2560, the servo motor, the soundbar, the webcam, the onboard PC, obviously the robot, and the monitor. So this is from last semester, and it's basically just showing like all the various connections that the we had to make in order for this our robot to work. So basically, the brain of the system is of course the computer. This will run the robot itself, and it'll also be able to control the camera gimbal, which though just showing the camera right now, it also includes the servo motor, the webcam, and obviously the gimbal itself. It will send data, visual data to the monitor and audio data to the speakers, and everything is controlled by the 12-volt battery, which will then go into the inverter, and then everything else plugged into that.
Alrighty. So, for the code progression. So this is kind of a layout of how it all went about to get the code ready. So we first created the flowcharts for the robot, which you've seen in previous presentations. Then we were to get the base of the robot to move, which was quite a feat because Visual Studios, apparently when you set it up, in there you have to put certain properties for the what's called the solution. And so that caused a lot of issues in getting it started. And then we moved on to getting the two computers to communicate via the server. It's a very simple base server, and basically what happened is it took us a little time because the for some reason the USB serial port that was being used by the aria.h library was interfering with the socket server. A fix for this was we found that the ARIA networking library that the robots, I guess producers, coders wrote also did a socket server, and it fixed that issue. Then we moved on to get one computer to send data to the other and move the robot. And that once we had both of 2 and 3 working, number 4 was not too bad. Then we moved on to building the Arduino code to control the gimbal, which Jasper will talk to you after I'm done about. And then we built the user interface, and we created the sensor detection code, which kind of works. And then we refined movement for the robot so that it was easier for the user to control. So a coding overview that you saw in December was this. It's a little bit complicated, it's color-coded, doesn't make a lot of sense. So this is the new current coding overview. Makes a little more sense. The robot server is in the middle because it's the center piece of the whole robot. So it controls the webcam, the robot, and the client. And sends feedback to the client. And then also what you didn't see in this last flowchart is you don't know what data is being sent between each one. And this is showing the data, which is commands. The client's getting feedback from its from the branch it's sending, and then the robot server is communicating with the robot using sending the commands it gets from the client, but also it's returning the sensor info from the ultrasonic sensors. So this is the old high-level user interface flowchart. As you can see, the user connects to the user login web page. The user puts in the password and username, and it checks if it's correct or not. And if it is, it'll connect to the robot and begin sending and receiving data. And then the rest of this, which is basically has the user try to input anything, and if not, it just sits there. So the current high-level user interface changes a little bit, and they're identified by the 3 red circles. So the first red circle up top, this is the computer running the server. So basically, what happened was the username and the password login page I didn't get to it, and so basically you just hit a button and then it'll connect to the robot. Unless it's not running the server, then it will not, and it'll just go back to its previous state. And then if it is connected, it'll connect to the robot, but it doesn't really send or start sending or receiving data. It just sends like, okay, we're connected. But past that, there really actually isn't any data being sent. 100% until the user starts pressing the button, and that's where we added this. Is look for feedback. So in the previous one, you can see it's just sending user to the input, or sending user input, but it's not actually receiving feedback. So that's where we changed there in the code. And then this is the old high-level robot server flowchart. So this is the server running on the robot. And one of the big changes that we have is, well, it's not really a big change, but we started the audio and video for the user earlier with Google Hangout because it's not integrated into the user interface. It's a separate window that you can pull off to the side. And so basically what happens is whoever is the, I guess, caretaker of the robot, they'll turn it on for everyone who's going to use it, and then they'll also connect to them using Google Hangout. So there's no need to put it down after asking has the user connected. So the current user interface. So the old user interface is this, what you saw in December, with an error log text box, look up and down buttons. It's fairly similar on the next slide, but the video isn't there, you'll notice. So, and it comes in two forms. So form 1 and form 2, you can see designated in the top left. And here's a big button that is what you will hit to connect to the robot. Now there is a IP text box where you would put in the IP address. It was a sense of security since I wasn't doing username and login that I was going to do. Unfortunately, it didn't work. For some reason, between passing the IP address between form 1 and form 2, it had an error, and so it would just resort to the local address, so it would never actually leave the computer. So now it's hard-coded into the button to go to that certain IP address that the robot's on. This is the actual user interface, as you can see. These buttons actually you can't click with your mouse. They're just feedback, so when you hit W or A or S or D, it will basically light up green. That's what it does, but the exit button actually does work. And then up here is the user interface text box. So that's like the error log text box here that you can see, but that's up here. And now I'll just read, when the sensors do go off, they'll be like, oh, you can't move forward, or you can't move left.
Okay, so I'll be talking about the Arduino, the way I work on the Arduino, and as probably many of you found out, we control the motor via the PWM pins on the Arduino, as well as the servo.h library. So we had initialized it to be a particular angle at the start of the when we plug in the Arduino, and that's just hard-coded in. So every time we plug it, the Arduino in, will automatically just go to that particular degrees, and then it won't move until you click I or K, which is the move the Arduino back keys. And each press of one of these keys will then move the Arduino by 1 degree each, forward, back. And this will then, it will move the Arduino between positive 45 and negative 45 degrees, and will go no further than that. And the Arduino will also receive signals from the serial port that is on the computer itself. So some of the programs that were involved between Jasper's and I's coding projects was Visual Studio's, Aria.h library, the Ario network library, which I discussed using for the robot server, Google Hangout. One of the things that got scratched was HTML JavaScript for the user interface. It ended up actually being easier to use C#, just because I was already using Visual Studios and it had already downloaded it, and it's a really drag and drop kind of deal. So it was just a lot easier to use an all-in-one program. And then we used the servo.h library for the Arduino. So the test report overview. So we're going to go over it real quick, and then we'll kind of go into why each one failed or passed. So the long distance video chat, it did pass. The user interface also passed. Unfortunately, our sensor test failed, although our speed test did succeed, and we'll get to why that kind of failed. It does work a little bit, but not as much as we would like. Tipping test, it passed when it goes over backwards, or when it goes backwards over a bump, or when it goes forwards over a bump and stopping immediately. It doesn't tip over, thank goodness. The webcam gimbal, it did pass the test and pass battery
audio, and then the connection test, it kind of failed hard just outside here, actually, in this corner, which will show a video.
So our long distance video chat, we passed, these are our SDRD requirements that corresponded with that test. All 3 of them passed. And then we go over to the user interface test. 2 of our SDRDs did fail, but we did have general connection between the user at a remote location and the robot at its current location.
Yeah, these 2 failed just because we don't have the username and password, but also the IP address. Since it didn't actually end up working to put in the IP address, it fails the test. So.
Then we moved on to the tipping test. That passed with flying colors. Thankfully, our robot did not fall over when put to extreme conditions. The sensor test did fail when the robot was in place and the sensors were triggered. The sensors were able to communicate to the rest of the computer that there's an object in the way. It did not move towards the object in that direction. But when the robot was in motion, it was not able to communicate to the robot fast enough, and the sensor ran to the object or whatever. The speed test, below you can see the Excel spreadsheet of our data. Me and Landon both took times, averaged together, and divided by the distance traveled with the robot. As you can see, we were well under 0.5 meters per second, which is perfect. You know, we don't want to go anything faster than that and risk damage to the robot.
So for the webcam gimbal, the robot camera mount had 1 degree of freedom up and down. It did fail, though the robot camera's mounts for the speed between 1 and 2 degrees per second. Okay. And I do not recall what we used to measure that, but from there we passed every other SDRD for that. The battery test, we passed both, it should be powered by a portable battery and shall use an effective battery that will allow it to operate through 2 class periods. During the time before and after our test verification class a week ago, we actually were testing that as well. We just left it on sitting out in the hallway, and it worked perfectly fine. But it did not pass having a basic wall battery charger so that it can be plugged into the wall because we just didn't have that charger for it. We've been using the robotics charger. The audio test, it passed. We put a decibel meter in, I think it was 159, and we sat there and we talked to it from the front of the classroom, the back of the classroom, and it met the requirements. And then our connection test failed really hard in, as I said, in the east hallway here. I'm going to play the video. So about right here, we lose connection, and then it just keeps driving into the wall. And there was no reason for it. We couldn't figure out why it kept losing connection there, but that was the only place in Gellerson that was losing connection. So some quick additions. We put in the username and login page. We fixed the hard-coded IP address, and we'd actually make the sensors work. And then the new PC, since we were running it with my laptop, we'd rather run it with an actual new PC so that you don't need my laptop to run it.
Some new additions or modifications that the mechanicals would have done. We would have added new training wheels, the side support wheels, and the base of the robot to make sure just the stability worked with our robot, not just with previous iterations. Holes for wires to run through on the stem supports, cleaning up the appearance a little bit. We would have used a different type of component case, probably with a little bit more money. We could have probably gotten an extra quality, but we were a little strapped for our budget at the end and chose to go a little bit of a cheaper route. And then finally, if we go back one slide, we would have added horizontal movement for the camera gimbal to mimic even more neck behavior. Finally, in summary of our presentation, we took you through the goal of our telepresence robot. We went through our SDRD requirements. We went through the mechanical, electrical, and computer components. We did a test overview. We talked about some additions that we've made, and now we have time for questions. Professor Alhai.
You said you know the issues that you have with the Wi-Fi in the hallway. Is it?
We
you don't know the issue?
Yeah, so Professor Elvike, if we asked if we knew the issue to it losing connection in the hallway, and we're unsure exactly, we'd have to test it more thoroughly to figure it out. I have a feeling that it's where it's transferring from one router to another, and it's just losing that connection for a quick second, and the socket server just can't handle it for some reason, because it sends a string of error codes, but it's hard to catch it and like look at exactly what it is that's happening. So we weren't able to figure it out entirely. We didn't. If we had more time, though, we would be able to.
Any other questions? No. Thank you guys. Plus you can like hide it or like stick it somewhere. Like it's different way to put it.
We're all gonna hang out in this corner.
Yeah.
Good. Good luck, guys. Thank you. Four? Do you have the? No, it's over there on the table. Yeah, the clicker. Sure. Thank you.
Hello, I'm Ryan Hudson. This is Ryan Taylor. It's Madeline Horton, Dylan Antonides, and Amanda Jacques. We are Surf's Up, and we will be presenting our final design presentation today for the solar reactor. To kick things off, I'd like to start off talking about an overview of the presentation you're going to hear. We're going to start with the feeding system and talk about the auger and line vac and the implication of the line vac. Then we're going to talk about the testing of the feed system. We will then go into the impact and reactor system, where we talk about the linear motor design and the design of the piston, and then we will talk about why we chose the piston, and then we'll talk about how we tested the piston, and then finally we will go into the collection system and talk about the outlet tee and the collection cyclone separator, and then we will talk about the testing for that, and we will end the presentation today with a summary.
So one of our main goals for our project was to increase the flow rate of cobalt oxide through the reactor up to 90 grams per minute or greater. So when the project was handed off to us at the beginning of last semester, our customer had raised some concerns to us that in regards to achieving this goal, that one of the limiting factors for this would be the existing auger feed system. So the existing auger feed system that was in the solar furnace utilized a 3D printed auger to dispense cobalt oxide. So at the end of their research over the summer, it had not been tested over 30 grams per minute out of fear of either breaking the auger, and also because the existing reactor would not be able to actually handle any higher flow rates. So they didn't really have a need to feed higher, and would in fear that they would break it. So to address this issue, our team decided we would first, so in addition to addressing some of the other issues with the reactor, our team decided to simulate and then test this auger just to make sure that it would actually meet the demand that we were going to be putting on it. So to do that, our first step was to make a model of the auger, just so we didn't end up testing it and breaking it. And in doing that, we wanted to make sure we limited the RPM of the auger to a max of 50 RPM. And also some of the other design parameters we used, just based on research we did online, was that we started with a range of 30 to 50% as an assumption for the auger fill efficiency. So from that model, we were able to we were able to generate these theoretical calibration curves shown here on the screen. These theoretically tell us that basically what the flow rate of cobalt oxide would be for different auger RPMs. And based on these curves, you can see that, based on these curves, we were able to determine that theoretically the auger should be able to feed up to the 200 grams per minute within our desired RPM range shown on the left. So since we had that result, we decided to proceed forward with actually testing the auger. And from that testing, you can see the testing from that is shown here on the screen. So from this calibration curve, you can see that we tested up to 100 grams per minute and generated a calibration curve for that. So the reason we stopped at 100 grams per minute was because that if we went any higher, the auger would start making additional new sounds and things like that, and we were feared that we were going to either break it. And also along with that, so that when we were testing our auger and kind of testing our whole entire system, we were also limited by the fact that some of our modifications were not capable of feeding up to that 200 grams per minute. So yeah. However, based on if we overlay actually the model of the auger and then the calibration curve for the 40% fill efficiency, you can see here on the screen that they actually line up very, very well. One thing to note though is that the model of the auger actually did not account for any additional feeding due to the vibration motor that's attached to the back of the hopper on the auger feed system. So I guess in conclusion, we were able to determine that the effective auger fill efficiency is about 40% for our auger, and it'll basically meet our applications. And required essentially no changes at all. So one of the other big, so the second area that we needed to address in terms of feeding cobalt oxide into the reactor was that the existing system was unable to actually handle that high flow rates through the inlet shaft of the reactor. So to address this, we chose to utilize a line vacuum to accelerate the cobalt oxide using compressed air into the reactor cavity. This had a few benefits besides just moving cobalt oxide in faster, in that it also generated a better cloud of cobalt oxide inside the reactor. So this, in terms of the overall goal of the reactor, which is to convert and perform the chemical reaction, it basically directly irradiated cobalt oxide with sunlight. So after all the testing and verification, we determined that when we run the line vacuum at 10 psi, it basically meets our objectives.
So the user controls the feeding system remotely through LabVIEW. There are 3 components here of the feeding system: the screw feed, the line vac, and the vibration motor for the hopper. So to make this better for convenience, we implemented an all-on button, which turns them all on at once. So you don't have to press every single button every time you run the experiment, which actually saves a lot of time on delay as well. So, but there was also the extra choice of running each one, each component by itself as well. The vibration motor for the hopper required 12 volts. So initially we had a 24-volt module switch in the compact Rio, but we needed to add an additional 12-volt module to control the hopper itself and any additional 12-volt applications in the future. We did find out that the vibration motor requires more current than the module gives it, so we had to order a relay, which is shown right here. And this allowed the additional current to be delivered to the hopper.
Thank you. So the addition of the line vac that Ryan Taylor talked about allowed us to easily reach the 90 grams per minute cobalt oxide feed rate that we were intending to hit. However, we were aware from the beginning of this process that adding forced induction of cobalt oxide introduced a risk of blowing cobalt out of the aperture of the reactor, a question that actually several of you asked during our OPRs. During preliminary testing of the linear, the line vac, we realized that this sphere was in fact founded, and we measured some cobalt oxide coming out of the aperture. So consequently created several designs for deflectors like the one shown here that we're going to solve this problem. They redirect the airborne particle, or the airborne mixture of particles, to the sides of the reactor and keep it from coming out of the aperture. A side benefit of this is that redirecting the particles causes them to reside longer in the reactor, increasing the chance that they fully convert from one particle or one form of cobalt oxide into the form that we're looking for. Several different designs were made for this, including two-dimensional circular and star-shaped deflectors, as well as a three-dimensional bowl-shaped deflector. The three-dimensional one was thrown out because of implementation concerns in terms of how we were going to mount it. And between the two-dimensional deflectors, the star-shaped one proved to be a lot more effective. So the way we've chosen to implement it with the two-bolt strategy means that if in the future the SURF decides to change the pressure at which we're operating the line vac, say if we do need to feed up to 200 grams per minute, you can easily remove this deflector from the front without having to take the cavity out, manufacture a new one, and bolt it in from the front, making future work easier to complete. This video shows the cloud of cobalt oxide that's generated by the line vac with the deflector in there. As you can see, it's pretty thick. And although it's not immediately evident from this video, the deflector has prevented that cloud of cobalt oxide from coming straight out of the aperture. Later on in the slides, I will present data that indicates how much cobalt oxide is being lost throughout the entire process.
So the next major system we worked on was designing an impact system, which purpose was to reduce the amount of cobalt oxide that's building up inside the cavity. So this picture shown on the screen is what the cavity looks like after an experiment we did on Sun at the beginning of the first semester. So this was before we had made any changes to the system. And so as you can see, there's a lot of cobalt oxide caked up on the walls. This was from an experiment where we fed at 20 grams per minute. So imagine now we're feeding at 90 grams per minute and how much buildup we're going to get on those cavity walls. And this demonstrates how important our impact system is to the success of our project. So we first designed the impact system to be a linear motor from Linmote. We selected this due to its wide range of controllability. So with this product, we would have been able to control the velocity, acceleration, and travel distance of the slider. However, we ended up not proceeding with this due to its high cost. This actually ended up being a really good learning point for me. So I started my research on the linear motor by contacting a design engineer from Linmote to get his advice on which model of linear motor to select. So this whole process of waiting to get contact back by someone, explaining our application to them, and then finally receiving a quote took a month. So, and the deciding factor was the cost. So if I would have gotten a ballpark idea what this product would have costed from the very beginning, we wouldn't have wasted a month of. So now that we know the linear motor was an option, we needed to design something new for the impact system. So we ended up going with a pneumatic piston. There was already an air compressor in the SURF, and it wasn't in use, but it had already been hooked up to the test stand. So we selected a dual acting piston, which allowed us to actuate the extension and retraction of it. The piston is actuated through two single acting solenoid valves, which we are controlling through LabVIEW. And then we also designed the mount of the piston to help us with heat transfer, since that was one of our big concerns with the piston. So like I said, the maximum operating temperature of the piston is only 200 degrees Fahrenheit, which is about 93 degrees Celsius, so this was a big concern for us, as the inner cavity of the reactor operates at temperatures at or above 1,000 degrees Celsius. So to help mitigate the heat transfer through the reactor to the piston, we installed quarter-inch insulation between the outer shell and the mount, along between the bolts and the mount, as shown in this picture here. We also are using a box fan for forced convection over the piston to help cool it. So to make sure these ideas were going to be sufficient enough, we simulated it in SolidWorks heat transfer simulation, which predicts a maximum temperature on the piston of 46 degrees Celsius. So this temperature has not been verified with an on-sun test yet, but the weather is looking a lot nicer now, so we're hoping to test this soon. So here's the control path for the piston. So as mentioned earlier, all the controls are done remotely in LabVIEW, which is on a computer outside of the room of the test stand. From LabVIEW, it connects to a compact reel, which is the industrial controller. And the industrial controller has several modules. One of these modules is the NI9472. So this one in particular is a 24-volt digital I/O module. So this acts as a switch for us, which connects to the solenoid valves, which then controls the position and velocity of the piston itself. So the impact system controls are composed of two things. One is the cavity rotation, so that's on the right, and that had actually been implemented by last year's group. The only change we made to it was switching from a sine wave to a square wave of the voltage inputted into the motor, and I'll tell you why that's important in a second. The second one was the piston motion, so that's on the left. There were two options for control, a manual control, so you can extend and retract at will, but for the experiment we needed more of a continuous cycle. So here we implemented a continuous thing. You have the option of selecting the interval as well as the pulse width when it's extended. So an additional factor was to reduce damage to the rotating cavity itself as well as the piston. We wanted to halt the rotating cavity when the piston was extended, so that was implemented as well. So the reactor rotation, initially what last year's group had done was implement a sine wave. So these are two graphs. The y is the angular velocity and t is time. So basically what's happening here is in the sine wave, it's going forward, slowing down, coming back. This is fine and all. It does mix up the powder a little bit in the reactor chute, but we really wanted to get kind of a jolt. And if you see here on the square wave, how it's very harsh, this creates a jolt in the reactor rotation itself, which actually knocks the cobalt oxide off of the walls. So it's not a huge difference, but it was enough that we made the change.
So this is our video of an off-sun test of our impact system all working together. So as you can see, the cavity is rotating, stopping, piston striking, there's cobalt oxide falling off the walls, and then the rotation is beginning again. So we haven't tested this on sun, but from our off-sun testing, this shows to be a very promising system that will either reduce or eliminate the buildup of cobalt oxide inside the cavity.
With cobalt oxide coming into our reactor more rapidly, we needed to update the collection system. And the collection system depends heavily on airflow, and to that effect, we need to update the outlet chute so that it's more airtight, but still takes in the cobalt oxide from the cavity and cold air to mix with the cobalt. So to achieve an airtight seal, flanges were welded onto the outlet T, and they're bolted together using 4 bolts. And an air intake gate is attached on the left of that, and that allows for the cold air to come in with the to cool the cobalt oxide. A camera was also mounted in the air intake gate. This is to visualize the cobalt oxide coming out and to visually see that it's red hot right before it's sucked away into the cyclone separator.
One of the most critical pieces of the collection system is the cyclone separator, which is necessary to continuously remove cobalt oxide from the airstream flowing through our reactor system. It operates using the same principle as a centrifuge, and the way we've placed it allows easy access to the cobalt oxide through the collection vessel shown in the bottom of the photo following the conclusion of an experiment. Downstream of the cyclone separator, we've included an inline filter for safety reasons. Although the cyclone separator has extremely high efficiency in separating out the cobalt oxide, we wanted to include this just to make sure that any cobalt oxide that's not removed from the airstream is caught in the filter rather than